Okay. So let's start a class for today. So now we're moving to the actual physics. We're starting the physics of this course. If because yesterday we kind of had a like a refresh um on vectors and some algebra of vectors. So that's gonna come handy, of course. And you have the homework enabled, so you can complete it, and it's gonna be due by this weekend. So I mean, it's pretty easy homework, so it's not gonna it's not gonna be very demanding in time, so you should be fine with that. Just if you have any problem or issue accessing it, just let me know. That's on Pearson's website. Okay, so moving on, looking at some physics actually. So we're gonna talk about motion along a straight line, right? Because we said last class that physics is enabling us to, let me get the pointer here. uh, Physics is enabling us to predict, right? So what we're going to talk about is predicting the motion of an object, of specifically a particle, because remember that we talk about the simplification, right? The modeling that we are getting into. So we are considering moving objects and things as particles for now. So let's just start with the simplest movement that we can imagine, which is a straight line moving at a constant speed. So we're gonna the subfield that we're gonna study is called kinematics, which is related to movement. That's basically movement. Um, um, so we're gonna describe motion. Um, and as I said before, we're gonna concentrate just on an object moving on a straight line. So we're gonna introduce the physical quantities velocity and acceleration. And bear in mind that these two quantities are actually vectors, right? Because when we define a velocity, of course, we can specify the modulus of the velocity. That will be the value, but we need to specify the direction because it's not the same thing going to the right or to the left, right? And then acceleration, same thing. Acceleration will affect the velocity, and it has to be a vector so we can determine how it's gonna affect the vector velocity. So let's start with displacement time and average velocity. So imagine that we start looking at a particle which is moving in a straight line, and of course I want to stress this several times because it's really, really important. Uh, the fact that we need to establish a system of reference. So here, our system of reference is just a one-dimensional system of reference, which is the coordinate system, and it's shown by this arrow here. So we have the origin at 0 and the x-axis, which is going to the right. So that will be our system of reference. We cannot specify any kind of movement or actually anything if we don't have a proper system of reference. And that's gonna come handy when solving problems. And it's gonna be part of your, let's say, grading, because it's gonna tell anybody that's reading your problem which is the strategy that you're applying to solve that problem. Because of course you can pick any kind of system of reference. You can tilt it, you can select a reference that's going to the other side, so that doesn't really matter. Physics is not going to change because the system of reference you have chosen. So but bear in mind that you gotta choose wisely, right? So if the particle is going from point 1 to point 2, uh, and it's going from left to right, so it's always more intuitive and better to choose a system of reference which is in solidarity with the movement that we're studying. So let's say we have this particle P1 P1, sorry, this particle at position 1, which is going to position 2 in a span of time. So we have T1 and T2. So that particle, we can say that it changed its coordinate by delta x. We're gonna refer to differences in quantities with this Greek letter, which is delta. So our delta x, our displacement, will be x2, the coordinate at the particle at the end of the movement, minus x1, which is the initial position of that particle. And let's keep in mind that the units of delta x are meters or centimeters or millimeters or whatever length unit you're using. We are going to use this kind of notation, which is with this parenthesis, to denote the unit of a quantity, right? So every time we write like this, we're talking about the unit that the quantity is represented by. Okay, so let's look at this. We can define the average velocity of that particle traveling from x1 to x2. What's the most intuitive way to do it? Okay, so speed, velocity, it's the quantity of length it's being spanned in time. So the most intuitive way to calculate it is dividing the displacement by the span of time that it took the particle to go from the first point to the second point, right? So if you take a look at that, we are defining the average velocity as the displacement over the time. And so we can check the dimensions of the velocity. So this is v AV, that's for average, and on the x-axis. So the dimensions of the velocity will be meters per second, meaning that if we have 1 meter per second velocity, or let's say speed, in this case, the particle is gonna move 1 meter per second of time. So from this we can say that if the displacement points to the positive end of your coordinate axis x, then the speed, the velocity is gonna be positive, and if the displacement points to the other side, the velocity is gonna be negative, because we can see that the velocity is telling us the actual direction of the particle in our system. This doesn't mean that the particle is on the other side of the axis, going over 0 to negative values. But it means that if the particle is going from x2 to x1, then the velocity, the vector, will point to the left, because that's where the particle is moving. Okay, let's move on. Everything good so far? Any questions about this? Okay. If you need to drop a question or something, just speak up or drop it into the chat box. Let's move forward. All right, so let's talk about the position time graph. So if we graph the position versus time, meaning that we have on the x-axis time and on the y-axis position, just be very careful when looking at this kind of graphs, because they are not the trajectory of the particle. That has to be very clear to you. So this is not the trajectory. The trajectory still is a straight line. So the particle is going from P1 to P2. And what we're doing here, we're graphing the position of the particle against time. So let's say the particle is at P1, and then the particle, car, or whatever. We have a car here. So it's moving from P1 to P2, and it's doing it in a fashion that the graph that we get, it's a curve, right? So it's not moving with a constant speed, let's say, in this case. So if we take these 2 points P1 and P2, we can say that the slope of this curve of this straight line is the average velocity, because remember, we're calculating, the average velocity as delta x over delta t. So if we take a look at that, we'll have delta t down here, like t2 minus t1, and then we have delta x with the displacement axis. It's x2, which is here, and x1. Right? So if we calculate that, we're gonna have the average speed that we defined on the previous slide. And if we take a look at the geometry of this, we have a triangle here, and this operation is giving us the tangent of the angle, and that's the actual slope of this side, which is the hypotenuse of the triangle. So let's think about how do we calculate instantaneous velocity. Because of course, average velocities are okay, but in order to describe the movement of a particle, we need the instantaneous velocity. We want the velocity at a specific point. We don't want just the average over the whole movement, because we need to know, we would like to know where the particle is. So we would like to know the speed vector. And in order to do that, we need to start thinking about reducing the delta x as long as we can, right? So the instantaneous velocity will be the velocity at a specific instant of time, and that concept of instant, that instantaneous concept, can be related with looking at the limit of the expression. I think you've seen limits and derivatives and integrals, right, in previous courses, or at least you should have heard about them. If not, it can be kind of tricky, but I guess you are all familiar with this math. So if we make this this delta x as small as we can imagine, so the time between those points will be as small as we can imagine. So we want the instant point, right? So this is gonna be infinitely small. So we can write what we have down here. So the Vx, so the instantaneous velocity of the particle, will be at the limit, and that we can get this interval of time tending to 0. So we want to make it really, really, really small. And by doing that, we are getting into an instantaneous point in the movement of our particle. So what this gives us, if you remember that from previous math classes, that will give you the derivative of the let's call it now a function, the function of position with respect of time, so dx dt, and that will be the instantaneous rate of change of the particle, this dt, which is delta t tending to 0. It's an infinitesimal small portion of time. Okay. Any questions about this? This is basically the fundamental expression of velocity, and it will be extrapolated to acceleration. So if there's any concern about how we are approaching this or the math involved in it, please speak up. Awesome. All right, so let's take a look at this graph. So we have going back, right, to the graph that we had before, which is the displacement against time. So let's say we have that car, which was, again, this is a particle or car or a moving object, which is going on a straight line. This is not the trajectory of the particle. So it goes on a straight line and it's changing its position at this particular ratio over time. And if we take the average speed, it will be as we said before, delta x over delta t, and that will be the slope of the the straight line, which is defined by P1 and P2. And let's say we have some numbers here. Okay, we can calculate the average speed as 150 over 2. That's 75 meters per second. If we take a closer look at a different section of the movement of the portion of time, let's say we get closer now. P2 is closer to P1, so now we can calculate again the average speed between those 2 points, and that will give us according to the graph 55, because it's going to be 55 meters over 1 second. But if we get closer and closer, then we have a point there, right? So if we have a point there, then this line, the green line, is gonna transform into the tangent of that curve that we have here. So remember, this curve is position over time. So this is xt, right? This is a function. So when we get to this point, the straight line on green here is gonna be the tangent at that point, and the slope of that tangent is actually the instantaneous velocity. So if we would look at this graph, just analyzing it mathematically, we could say that the derivative at the point P1, it's gonna be the slope of this straight line. But we're in a physics course, so this thing has meaning to us, and that means that the slope is the instantaneous velocity. Okay, so let's take a closer look to this graph here. It's fairly interesting, so we can think about what we've reviewed with this other graphs. So we have a particle, remember, which is going on a straight line, but the trajectory is not as happy as this one, and the way the trajectory is a straight line, right? But the way the speed changes, the position changes, sorry, the position changes is different in this case. So we have at point 8 where if we draw the tangent there at point A, we'll see that the slope is positive, meaning that we have a speed which is positive. And that would mean that, let's say we have a mobile going up, right? So the particle will be moving up if we have let's imagine we have our coordinate axis pointing up, so it's going to be positive, so it's going up the particle. Then when we pass through B, let's say that we keep that slope positive, so it's still going forward, still going up, until it reaches some point up here where, as you know, the horizontal, right? So the tangent of a horizontal is going to be 0. So the instant speed is going to be 0 at that point. What that means that at that particular instant, the particle is stopping. It doesn't have any speed. It's stopping and then it's coming back. When it comes down, means that it's the particle is going from higher, let's call it higher modulus positions to lower, so that it's going back. So the particle that is going up, 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 up until it reaches C, stops for an instant, and then starts going down again. So now you see that we have a negative slope, and that negative slope is it means that we have a velocity which is negative, meaning that it's moving against the coordinate axis we defined. Okay, let me stop here for a second and let's take a look at some problems. Okay, let me enable the tablet. We're gonna take a look. If you have the problem sheet, we're gonna take a look at problem 1 of set 1, which is motion in 1 dimension. Let me pull it up. If you have any questions, please drop them or place them. Okay. Can you all see the screen? Just give me a quick thumbs up or something so I can make sure that. Awesome, thank you. Okay, so this is problem, as I said, problem 1. So it's the first problem of set 2, which is called kinematics. And just we're gonna go real quick over this first problem and problem, let's see, problem 2, so we can take a look at this in a better practical way, you know. Okay, so this problem is asking to take a look at the function, and I'm just gonna read it just in case you should have it, but just in case. So it says the graph represents the position as a function of time of a particle moving in 1 dimension. So basically what we've seen so far. Relate the data provided by the graph with the concepts from the theory and determine A, the function of xt. So we want to determine the function that it's gonna mathematically describe the displacement of this object. So let's see. For starters, we can tell that this is a straight line, right? So we know that the function. Oh, let me get the blue one here. The function would have a form. Right, this is an M like this, right? So we have mt plus something that we will call h. So we have our variable, which is time, that's t, and we have the slope of that straight line, and we have some displacement, which is h. And if you remember from math class, that displacement it's representing the the offset that we have with respect to the x-axis. So what we can do to find out how the value of h, we can do x at 0 time, meaning that we're looking at this point right here. So we don't need to do much calculation here because we know that that is mt equals 0, right? Plus h, and that's going to be 20 meters. So that h is basically 20 meters. That's the offset that we have, the starting point of the movement. So this particle is starting its movement shifted 20 meters from the 0 of our system of reference. Let's say we have our system of reference, something like this. So the x-axis is there. So the particle is starting to move at 20. Let's say the units are meters. And this is 0. So again, this is the trajectory of the particle, a straight line. And this is the graph of the function, which is representing that movement. Okay, and let's see. So we need to calculate m in order to specify that function. And in order to do that, we can do m equal the tangent of alpha that we have there. And for that, we can take any two points that we want to compare. We can take any point to compare that specific triangle. So let's say we have, the value at 30. So it will be 30 minus 20. And that's 1 minus 0 seconds, meters. That's 10 meters per, oh, sorry. I almost dropped the tablet. 10 meters per second. Okay, so now we can actually tell the functional form of our displacement, which is 10 meters per second t plus 20 meters. Sorry. Is that clear? Any question about that? That's the way we can specify the function of the movement. Okay, so far we haven't said anything about velocity or anything, but we will get to that. So what's the direction? Which is the direction that the particle is moving? That's the second question. So from what we can see here, the particle is going from 20 to whatever position after that. So if we established an axis like this here, which is respecting the positive values that we have in our axis position here, so the particle will be moving to the positive side of x. Okay, let's look at the C question C. The initial position. Well, this is fairly easy. We already talked about this. So the particle, it has an offset, so it's not starting at 0. So that x0 would be x at time equals 0, and that's 20 meters. D is asking the particle velocity. Well, mathematically, we already we already calculated it, which is, as we said before, the velocity will be the slope of that straight line, and the slope is 10 meters per second. So velocity 0, or in any case, velocity, because it's constant, it will be 10 meters per second. Well, let's see E. So, of course, well, what does the slope of the graph represent? Well, that's actually what we just said, right? The velocity. So, slope M, it's representing the velocity. And then what type of motion is this in terms of the acceleration? Do we actually have acceleration? We haven't specifically talked about acceleration, but we know that when we accelerate, what happens? Velocity changes. And in this case, velocity is not changing at all. So let's say it's a straight line uniform motion. Okay. One thing we can do, we can take from those two questions here is the way we are actually writing the position over time. So if you take a look at that, we're gonna have xt, it's gonna be x0 plus v0 t. When this thing is constant, then we have a straight line uniform motion. Okay, any questions about that? Okay, let's take a look at exercise 2. Let me go back, problem 2. Problem 2 says a commercial plane takes 35 minutes to fly between two cities separated by about 520 kilometers in a straight line. Obtain the average velocity in kilometers per hour and meters per second. So basically, I mean, it's fairly straightforward, this problem. So the plane is going, let's say, in a straight line with a speed equals a velocity equals to 520 kilometers, right? And it's asking oh, sorry, yeah, it's not speed, it's the displacement. Displacement. So let's say it goes from A to B. So displacement is that 520 kilometers over a span of time, which is 35 minutes. Yes. And so it's asking us to calculate actually the average velocity. So we can write the average velocity. Let me just economize writing, so it's just v. So this is going to be delta x over delta t. And if we write this, it's going to be 520 kilometers over 35 minutes, right? But the thing, the problem is asking us to express it as kilometers per hour. And how can we do that? We can multiply by something which is equivalent to the magnitude that we are looking at. So what do we need here? We need to, let's say we want kilometers per hour, then we need to transform this minutes into hours, right? We already have kilometers up there. So we can do 520. 520 is always, it's already there. We can do 1 hour. We need hours down here. 1 hour. And then we can do 60 up here. Minutes. Right? So this is actually a kind of a 1 in our calculation, not mathematically speaking, but quantitatively speaking, right? Because it's equivalent 1 hour, it's equivalent to 60 minutes. So we're just changing the units here. So let's say we get rid of those minutes there, and that's gonna give us, I have the numbers right, 891. Oh, please, guys, check. I mean, of course the answer is there, but you know, sometimes you can mess up with the calculations with the calculator, of course, or you know, messed up some numbers. So please check while we are doing the problems. So that's 891.432, if I got it right, which I think kilometers per hour. Let me. Yes. Okay. And okay. Any doubts about this? Any questions about this? Because this is pretty useful when changing when changing units. Because basically, I mean, sorry, yeah, 891.432. Yes. Let me get the 8 straight, maybe. Sorry about the handwriting. Okay, let's take a look at the other question here, which is having it in minutes per second. So for minutes per second, we can do the same, we can apply the same reasoning, which is delta x over delta t. And that's 520 kilometers, 35 minutes. Same thing. And now what we need here is meters per second. So we need to change both basically. So we need kilometers at the bottom. So we have 1 kilometer, right? And we have 1,000 meters up here. And we need to go for minutes. So we have 1 minute and we have 60 seconds. So we need seconds down there. So if we just get rid of those, get rid of these two, then that will give us 247.62 meters per second. Okay. Awesome. Okay, so what we've done here is basically transforming, of course, calculating the average speed, which is the displacement over time, and then transforming into different units. We could have done this just, like, of course, the mathematical operation is the same thing, but we can do, the linear relationship we have. We can do, let's say, if you just want to go like step by step, you can do 1 kilometer, 1,000 meters, 520 kilometers, x, and then you calculate 520 kilometers times 10,000 meters, and then you do 1 kilometer here. So this is basically solving, the linear relationship of those quantities and then plugging them into your equations. But as you can see, it's basically you're getting the same mathematical operation. And if you do that with the minutes and seconds, you'll get these other operation here. So just keep that in mind. This is no magic trick at all. It's just economizing writing and actually reasoning with units, which is very, very important in physics. The dimensional, this is not strictly dimensional analysis, but working with dimensions as with this algebra is pretty useful and good for practice. And of course, we want speed, we want the velocity to be meters per second, so we can actually check that we got meters per second or kilometers per hour or whatever length over whatever unit of time we're using. Okay, let me go back to the PowerPoint. Are we clear? Are we okay with this? Any questions about the problems? Because I'm gonna switch to the PowerPoint. Okay, cool. Stop sharing here. Okay. Let me enable sharing. Okay. Okay, so going back to the PowerPoint, we're gonna continue a bit with this topic. So let's remember that we stop at the we'd stop with the graphs of position over versus time, which was showing us how the particle was changing its position over time specifically, right? But it's still a straight line. I'm not gonna get tired of stressing that this is not the trajectory, because I always see it after in the exam. You're mixing the trajectory with this actual graph. Okay, so let's talk about acceleration now. Acceleration, as we said, describes the change of velocity with time. So we can apply, I'm gonna go a bit faster now because it's pretty the same reasoning. It's the analogous reasoning from the last few slides. So we can define the average acceleration as the changing in speed over time. So we can define delta V. We're carrying an X here because we're talking about just one axis, but it's delta V over delta T, and that's defined as the final velocity minus the initial velocity over final time minus initial time. And the units in this case, please take a look at this. The units are, sorry, just a second. The units in this case are meter per second over second. And what does that give us? That's meters per square seconds. So that's the unit of the acceleration. Okay, so same thing as before. We can define the instantaneous acceleration as taking the limit of that delta t to 0, right? So delta t goes to 0. So we are looking at instantaneous point in time over time, and that will give us basically the derivative of the velocity with respect of t. So a is equal to dv dt. And if we graph now, please pay attention to this, that now this we have velocity here and we have time here, so it's not position anymore, we're graphing velocity. So velocity will have a specific shape of a function, and then we can do the same analysis, take 2 points of that change in velocity, make the distance between them really, really small in the graph, and then the slope that we get is going to be the instant acceleration, right? So the average acceleration for 2 points, and when we make it very, very, very small, then we can say that the tangent, the slope of that tangent straight line at that point is the acceleration, which is the derivative of that function. So we can take a look at this VT graphs, and it's basically it's very similar to what we discussed before. We can take a look at the slopes. So we have a positive slope in point A and point B. So that means that we have a positive acceleration, but keep in mind that now velocity and acceleration can have different um, directions, right? So let's say the particle is moving towards 0 on the positive x, and it's moving towards 0, and the acceleration is opposite to that velocity. Oh, what does straight line? Sorry, because I don't get the notifications of the chat, but what does straight line motion mean? Does it mean that the acceleration is 0? Well, not specifically. Straight line motion means that it's moving on a straight line. So you can have a straight line with acceleration, actually. So that doesn't mean that you don't have acceleration. I mean, you can see it here, right? You can see it here. So the thing is moving on a straight line, but it has acceleration, and it's decreasing the velocity. And at some point, let's say B, the velocity gets to 0, and then you have positive acceleration. You still have positive acceleration. You haven't changed the direction of the acceleration. And now the object, the particle, starts accelerating. So speed starts going from 0 to some value. So it keeps going until it reaches C, let's say here. So we have some maximum velocity, because it's an inverted parabole. We have some maximum velocity, and at that point, the tangent is actually the slope. It's actually 0. So no acceleration there until it keeps going until it reaches D. So it crosses the so it crosses the t-axis, and at that point we get negative slope of the acceleration. So now acceleration is pointing this other way. So the object is starting to gain speed, pointing towards the negative side of the x-axis. So just keep in mind that we are looking here at the trajectory of the particle, which is moving, back and forth, and here we're looking at the variation of velocity over time. So this curve has nothing to do with the trajectory or the actual position of the particle. We're talking about the magnitude and direction of the speed. Okay. So now we can go back and take a look at that graph, which was quite, I wouldn't say complex, but more complex than just a straight line or a parabole. And then we can analyze that and take a look at the different points. So we have the particle, which is starting at some point, let's say here at this position with that speed. So it's moving to the right, and then it has some acceleration. We have the curvature upward, meaning that if we graph the speed, then we're gonna have acceleration, because we're gonna have a value in that tangent, and then we keep going until we reach point B, where we can say that we have acceleration 0, because we're gonna see that the curvature is 0 and the slope is gonna be positive. So we have positive velocity pointing to the positive end of the x-axis. if we keep going until we reach C. So when we reach C, we're gonna have velocity 0, because we can see this is horizontal, but we're gonna have acceleration because there is a curvature here. So if we graph velocity against time, this is not gonna be a horizontal line, right? And then we keep going until we reach acceleration 0. So we can say that the curvature there is 0. This is an inflection point, just like B here. So there is a change in the concavity of the curve, right? And then if we take a look at point E, we still have negative velocity, and we have positive acceleration. So we have a curvature which is upward. And I just dropped this thing up here because this is one of the other fundamentals of motion, which is basically defining the acceleration as the derivative of the function of speed with respect of time. So acceleration, as we said before, is dv dt, and that's basically, if we recall the previous slides, that's dx dt, and that's applying the derivative to that derivative. So this is a second order derivative of the position, and that's a fundamental thing to bear in mind. So we can relate acceleration, the function of acceleration, so at, to the position function that we defined at first. So this is telling us that if we have the function form of the position, we can apply the derivative, so we can derive the velocity. And if we do it again, we can obtain the acceleration. Okay, cool. Let's keep going. So we've graphed position over time, we've graphed velocity over time. So if we graph acceleration over time, in this case, we are talking about a motion with constant acceleration. So the graph is going to be fairly straightforward, fairly simple. So it's just going to be a straight line, at least in the cases that we are analyzing so far, because we're talking about constant acceleration on a straight line. So you can tell that slope is going to be 0 of this thing. That doesn't have any physical meaning in particular. And then the area under this graph is actually gonna be the change in velocity over time, right? Because we can calculate that as Vx minus V0x over the time span, which is basically the area of that rectangle. Okay, I think we've gone through this too, so I'm not gonna stop on that. Let me, yeah. So what's interesting about this, what it's important to note about the fact that we have constant acceleration, the fact that it's constant is not that doesn't really mean that the position is going to change constantly, right? So the sense of something being constant, just I want to stress that a bit. So if we take a look at this succession of graphs that we have, so we're going to have acceleration at first, let's say at time 0. So the particle is changing its velocity from 0 to something. If we keep the same acceleration, that means that the velocity is changing at the same rate over time. So if we go at a different instant, let's say t, so we have delta t, then we have the acceleration which has increased with the the velocity has increased with the ratio that acceleration is giving us. So if we take a look at the same portion of time, let's say 2t, now the position is not going to be doubled, but it's going to be more than that, because the velocity is changing on each step that we're taking, which each step of time doesn't really matter if the time steps are equal, right? Because the acceleration is changing the velocity, and then the velocity is changing instantly at every point in time, and it's changing the ratio that the position changes to. So this is a nice example that if you have same portions of time and you have acceleration in that motion that you're analyzing, then the position is not going to be linear at all. It's not going to vary linearly, although the velocity is. Okay. So now we're gonna take a look at the equations that are going to describe the actual motion of a straight line, of a particle on a straight line with constant acceleration. So of course we want to be as general as we can be, so we can apply our function to any kind of, again, straight movement with constant acceleration. So when ax is constant, the average acceleration equals to the actual acceleration for the whole movement, of course, because it's not changing. So we can say that, we can just say that this t1 is 0, and we can get rid of those ones there and just call them initial values. So most of the times, the initial value that you're taking for time would be 0, unless you need to compare, two particles or something in particular, but it's going to be 0. So you can write the instant speed as the initial speed plus the acceleration, which is constant, times t. So if you recall from the problem we just solved, problem 1, we wrote the position in a very similar way for a motion that has no acceleration. We had position, initial position, plus velocity times time. So it's roughly, I mean, it's, of course, it's the same thing in terms of mathematically speaking, because we have a constant slope here. So it's basically the same math. So now if we do the same thing, do t1 equals 0, t2 equals t, x at t0, we call it x0. That would be the initial position, and our final position would be just x, just for the sake of clarity when writing. Then we can go back to the average speed that we talked about before early in the class, and then of course, we can write this average speed as the initial speed plus the final speed divided by 2, because that's basically the average, right? And when we substitute 1 into in 3 and equate with 2, we can get to this expression down here. And this is the expression of the position, the function of the position over time. It's gonna have the initial position plus the initial speed, or velocity, actually, the initial velocity times t plus 1/2 of the acceleration multiplied by t squared, right? So if you want to do the math, you can do it. It's pretty straightforward, but there's no need to memorize this at all. Of course, you end up memorizing after solving a bunch of problems, but this is it's pretty straightforward when you can integrate. So I think we go over that in the next class, but just keep in mind that this is very consistent and it's not coming from just combining equations. I'm just showing you first on this first glance of this expression, the way you can calculate it from the derivations, the deductions we've done over this past slides. And okay, as I said before, we have this marvelous, beautiful expression for the position over time that will tell us all the information that we need about a straight motion with constant acceleration. So we can again take a look at an example of a car moving straight forward. So so we can graph x with respect to t, and we see that we have the slopes, and we have the speed, initial speed, and the slope at the initial point. We have the final speed and the slope at this final point, and then of course the way the velocity is changing over time. That means that the motion is accelerated. It's changing. It doesn't mean that it goes faster. It just means that the velocity is changing. So remember, the velocity is a vector. So it has modulus, and it has direction. So acceleration is a vector too. So it has modulus and direction. And that direction will determine the way the velocity, the vector, the velocity is changing over time. Okay, so I want to present you these two expressions which they come really handy, and they're not coming from any specific magician hat or anything. It's just deriving from the expressions that we had before. So solving one for t, meaning that we can, let me go back here, we can express t, right, as vx minus v0x over the acceleration, and then we can plug that in our expression for, which is this one. We can get rid of time, right? If we get rid of time, then we have an expression which is relating the final velocity with the displacement we have here, x minus x0, and the acceleration and the initial velocity. I recommend you do that exercise. It's pretty simple. We can go over it in office hours or maybe next class. But it's a very useful expression because it's letting you calculate things without having time in the middle. And then we have this other expression here, which has, I would say, less utility than this one, the v² expression, which is just equating 2 and 3. I'm multiplying through by t. So again, you can do that for the, as practice. It's good practice for algebra. It's just, I would say, 4 lines of calculations. It's not that much. But you can relate the delta x, you can relate the displacement, the position at time t of that particle, the initial velocity and the final velocity and time. So as you can see here, we don't have the acceleration in the middle. So it's just a way that we can get our strategy right to find the values that we want, that we need for our problem. Yes, so that's I'm gonna stop there, and that's gonna be all for today. I recommend you take a look at the problem 5, which is gonna let you Yeah, problem I5. So it's motion in one dimension, problem 5. That's two cars that are encountering at some point, and you need to calculate how they where actually the encounter time. So that's gonna be good practice to apply what we've seen today. And then I would tell you to take a look at problem 2, or maybe we can go over that on the next class just to wrap up this, and then we can move forward with free fall. Free fall is gonna still be a straight motion, but now we have to take into account gravity. um, but of course gravity is just accelerating things, so it's the same math, nothing is changing, but the fact that we have by the fact that we have a free fall and not just one particle moving on a plane. So let me sorry, let me stop the PowerPoint and get this back. I stopped the camera actually because I'm in the office and I don't really trust internet that much, and you know, I can have issues with casting the tablet, the camera, and the screen at the same time. So any questions about basically anything about the class? No, nothing. Okay. That's if that's all, yeah, is the Zoom link for discussion the same as this one? Well, no, the Zoom link is different. Kate made a different one. It's posted on Brew and Learn, so you can just go there and click. It's a page. It's on the home page, I think, or I think it's there. But it's surely there. Yeah, it's different. Any other questions? Okay, awesome. I'll see you in my well, I'll see you all tomorrow, and remember my office hour for today is at 1 p.m. Thank you all. See ya.